Death from space, gamma ray burst. She has done her graduation from BAR Janta College, Haryana, her master's from Kurukshetra University, and at present she is doing her PhD from ARIES Nanital on the topic high energy transient, mainly gamma ray bursts and their associated counterparts, under the supervision of Dr. Kuntal Mishra and co-supervision of Professor Lalan Yadav. She has also been the coordinator of Young Astronomer Meet. I welcome you, ma'am, on the behalf of our Physics on Friday team and our whole department.
Hello, Dimple. Hello, Dimple. Can you hear me? You're muted.
Hello, am I audible?
Yeah.
Yes.
Yeah.
I'm sorry, there is some network problem at my end. Let me share the screen. Uh, okay. My screen is visible to you all.
Yes.
Yes. Thanks. First of all, thanks to all of you for inviting me for giving me this opportunity to present my work here. And my name is Dimple. I'm a senior research fellow at ARIES Research Institute of Observational Sciences. My work is mainly focused on high energy transient, mainly on gamma ray burst. So today I will give a brief introduction of gamma ray burst to you all. So before going to the gamma ray burst, let me recall what are gamma rays. So you might have seen this spectrum many times, when from radio to gamma rays. So okay. So gamma rays are the most energetic form of light with very small with smaller wavelength of the size of atomic nuclei. You might have read about this you can see where the count peaks.
This meeting is being recorded.
Okay, where the count peaks for a few seconds, for a fraction of second. At the right, you can see it outshines the whole universe. So these are so energetic events. You can have an idea from this. Okay, but as I already mentioned, that gamma rays can't penetrate through the Earth atmosphere.
Hello, Dimple. Hello.
Hello, am I audible now? Hello.
Hello, Dimple.
Yes, if I'm audible?
Yeah, you're audible, but your network is not good.
I need to shift somewhere else. Okay. If my screen is visible to you all?
Yes.
Yes. Can someone confirm where I have left the discussion?
You have to start from starting, I think.
Oh,
We
okay.
lost you from starting.
Okay, so let me start from the very first slide. I'm sorry for the inconvenience. There's some network issue at my end. Okay. Okay, let's start with the introduction to the gamma rays. So gamma rays are the most energetic form of light. These can't penetrate through the Earth atmosphere. And another thing is that the radioactive decay are the origin. On Earth, you might have read that the radioactive decay are the origin of the gamma rays. And the second thing, they can't penetrate the Earth atmosphere. And most of the gamma rays get absorbed in the upper layers of the Earth atmosphere. Now, these 2 points will be useful to understand what are the discovery of the gamma ray burst and the origin of the gamma ray burst. Now, let me introduce the gamma ray burst. Gamma ray bursts are, as the name indicates, these are the bursts that for these events, this lasts from millisecond to thousands of seconds. And the gamma rays, as I already mentioned, these are the highly energetic radiation. For these events, this energy varies from tens of kilo electron volt to several giga electron volt. Now, these are the most luminous events that can outshine the whole universe for a few seconds. You can have an idea how energetic these events are from the fact that if 100 of they emit the energy equivalent to that 100 of suns will emit in their entire life, they emit that energy in a in a fractions of second. Now you have an idea that how energetic this is. Let us have some glimpses of gamma ray burst, the happening of gamma ray burst. In the right, you can see the light curve of the gamma ray burst. X-axis is time and y-axis is count per second. You can see as the counts increases, and in the left, it is the map of the universe. You can see as the count peaks, it outshines the universe for a few seconds. Now, as I mentioned, how these events are discovered. Were we already aware that these kind of events are happening here and there in the universe? Uh, but we were not aware of it. And also, these gamma ray can't penetrate through the Earth atmosphere. It means we need to launch a satellite to monitor these bursts. Okay, but but as we were not aware, to launch a satellite, we should be aware where it is happening and why it is happening. We should be already aware for these events, but we were not aware of that. This all started with an accident. So what was that accident? These were discovered by the US Vela nuclear test satellites in July 1967, and these satellites were launched to monitor to have an eye on the nuclear test treaty that was signed by Soviet Union and US to ban any nuclear test throughout the world and in the outer space. So to have an eye on the nuclear on this treaty, they launched a pair of satellites known as Vela nuclear test detection satellites to have an eye on this treaty. But they discovered intense flashes of gamma ray, and they localized these events. And one by one, there were 16, 17 events. One by one, they detected using these satellites, and they found that they are not coming from the Earth. After localization of these events, they are coming from the random locations of the sky. So this is the first gamma ray burst ever detected. So this is the first light curve of the gamma ray burst. Okay, so the first paper that confirmed that these are not coming from the Earth from any nuclear test. They are coming from the sky, and they have cosmic origin. They are related to astronomy. The paper came in 1973. They reported that 16 short gamma ray short burst of photon energy ranging between 0.2 to 1.5 mega electron volt were detected between 1969 to 1972. And the directional information of these events eliminate that they are either coming from the Earth or coming from the sun. They have astronomical origin. Then lots of paper came on this for these events, on their energy spectra, on their origin, that if they have cosmic origin, or if they are coming from the solar flares, or from the dust, or if they are connected with the supernovae. So the big question was at that time that what is the origin of this gamma ray burst? Earth, Sun, Milky Way, our galaxy, Moon, or these have some cosmic origin. Now, what can be the solution of this question? We were we could localize these events, but the distance measurement cannot be done for these events. So unless we know the distance of these events, we can't say that if it is coming from the Milky Way, from nearby galaxy, or if they have cosmic origin. So this puzzle was solved by the detection of afterglows. Now let me first introduce you to the afterglows. What are the afterglows? So you might have seen the embers after a strong fire. You might have seen the embers, and they stays for a long time. So the same idea was given for the gamma ray burst, that after gamma ray burst there should be afterglows which can be detected in lower energy range. So the first afterglow was detected after the 30 year of the discovery of gamma ray burst. So in 1997, they detected the first optical and X-ray afterglow, and after that they solved this puzzle that if they have cosmic origin or they are coming from the from our galaxy itself. Now, how optical afterglows help them to solve this puzzle. Now, let me take a break. Now, you can see on the screen that it is a gamma ray burst 970228. Now, let me tell you what is the naming of how we name the gamma ray burst. So this is GRB. So the first two numbers tell us about the year of the happening of the GRB, the middle two about the month, and last two about the date. So this GRB happened in 1997 on 28th Feb. So this was the first optical afterglow detected. And now, why optical afterglow are useful for us? What they have done? So the optical afterglow can be used for the distance measurement. And once we know the distance, the exact location of the GRBs, we can have other property like host properties, and we can have their origin, how far they are. If they have cosmological origin or belongs to our galaxy, we can have that information. Now, you must have read about the Doppler effect in the sounds. As the source moves away from us, the sounds get the frequency get decreased, and as it come towards us, the frequency get increased. The sound frequency. The same happens in case of light. As the source receding from us, it shifted towards the redder wavelengths, and as it moves towards us, the frequency get shifted to bluer side. So as the universe is expanding, so from the we can get a connection between the redshift and this shifting in the wavelengths of light and the distance. So that is how we calculated the distance for this event using the optical afterglows. In the lower panel, you can see an example of this. This is the flux for in the rest frame, the blue one, and this is the original spectra of some of the event, and it is shifted towards the redder side. This is how we calculate the redshift of the astronomical events, and that's how we calculate the distance. And after the discovery of optical afterglows, and after the determining the redshift, we come to know that they have cosmological origin, and their redshift varies from 0.008 to 9.4. Now, to have an idea how redshift is connected to distance, a redshift of zero point 0.1 corresponds to 10 raised to power 24 meter. It corresponds to a 10 billion of the light years. So you can have an idea how far these gamma ray bursts are happening from our galaxy. And using the distance measurement, we can calculate the isotropic energy for these events. This is around 10 raised to power 48. This varies from 10 raised to power 48 to 55 Earth. That is thousands of times of the solar that the sun will give it in its entire life. Now we come to know that they have cosmological origin. They are very far away from us. They are highly energetic. They are multi-wavelength phenomena. They give emission from gamma rays to optical and radio in the lower wavelengths too. Okay. Now we know these much things about the gamma ray burst. Now let's come to the classification of the gamma ray burst. We have detected so many thousands of events till yet, and then we come to know there are two kinds of events. The two kinds of gamma ray burst. One is short gamma ray burst, another is long gamma ray burst. In the right panel, you can see the figure. Here it is the distribution of duration of the burst. The y-axis shows the number of bursts, and x-axis shows the T90 the duration of the burst simply. Now this so that there is bimodality in their duration distribution, which shows, and that is dividing it at 2 seconds, which shows that there are two classes of the GRBs. Further, they have checked other properties of the gamma ray burst, and so that observed that the gamma ray burst with time period less than 2 seconds emit more in higher energies as compared to lower energy. That is known as hardness ratio. So they classified it in the two classes. One is short gamma ray burst, another is long gamma ray burst. And further, they investigated what are the origins of these two bursts, from where, how they emit this much of energy, from where they are originating. So for the long gamma ray burst, which give emission less than for duration of greater than 2 seconds, from 2 seconds to 100 of second. So the most prevailing hypothesis for these bursts is that they come from the death of massive stars. When a star collapses, it gives emission in gamma rays, in form of gamma rays, and further.
Dr. Dimple. Dr. Dimple का है.
Oh, is it Dr. Dimple? Okay. Okay. The event that supports this hypothesis is the association of long gamma ray burst with the supernovae. So whenever a star explodes, it gives another transient, that is supernovae, and many of scholars in ARIES are working on supernovae. You might get some talk in the upcoming week on the supernovae too. So supernovae are the explosions when a star deaths, a star collapse. So you will get some more information from the supernova guys in the upcoming. Now coming to the short gamma ray burst. So the most prevailing hypothesis for the short gamma ray burst that they come from the collapsar, from the merger of two compact objects. Now, what are the compact objects? They can be the black hole, the neutron star, white dwarf. With the smaller size and containing a huge mass are the compact objects. So when these two compact object merges, as you can see in this figure also, when two compact object merges, it gives rise to the gamma ray burst and gravitation wave. So we find an evidence for this, because when they merges, they produce gravitation wave also. In 2017, you might have heard the news that they have detected a gravitation wave in 2017, and that was associated with the short gamma ray burst that give an evidence that they come from the compact object merger. So now it is clear that gamma ray bursts are cosmological. They give huge energies. They are lying at very huge distances. There are two kinds of gamma ray burst. One is long, other is short. Long are coming from the death of massive star, and short are coming from the compact object merger. Now, how do we come to know about happening of a GRB? What do we do when a GRB happen? What do we do? How do we come to know about that a GRB happened? Because as I mentioned, these are very short events, and they give afterglow in optical and radio too. But optical we can see only for 1 or 2 days. So to follow up these GRB, we have to be very attentive to detect these GRBs. So how do we come to know about the happening of GRB? There is a GCN circular, there gamma ray coordinate network. Whenever a satellite, there are multiple satellites that are dedicated to search for these kind of transients. So whenever a satellite detects a transient, it the location and coordinates and information about the GRB to one of the station, the gamma ray coordinate network, and this information is immediately given to all these searchers working on the gamma ray burst, and we will have immediately we have the information of coordinates of the gamma ray burst, and as soon as we get the coordinate, we move our telescope in that direction and get the optical afterglow, and using the multiwavelength data, using the modeling of that, we get the parameter, and we constrain the progenitor system of the gamma ray burst. So this is ARIES. This in this diagram you can see this there is a white colored dome. So it is 40-inch telescope. If someone has visited ARIES, you might have seen this telescope. So this is 40-inch telescope. As soon as we get the coordinates of GRB, we move this telescope in that direction and get the get the data in optical regime. Apart from that, we have three more telescope, 3.6 meter dot, 1.3 meter depot, and ILMT. We use these all the facility for the detection of these kind of these transients and work on that. So this is what we work in the ARIES. This is the field of my research, and that's how we do utilize the telescope for this purpose. Okay, thank you. If you have any question, you can ask.
Thank you so much, ma'am, for such an informative lecture and such an interesting presentation. Now, if anyone has any query, they may ask. Anyone? Anyone online, they may also ask.
Hello, Dimple.
Hello.
Hello, Dimple.
Yes.
I have one question regarding your that short and long GRBs.
Yes.
Ma'am,
Yes.
can you please tell me that is these GRBs are occurring daily, or there is some special days or even that?
Okay. These are the random events occurring in the sky. So on average, one event occurs in one day. So and if there are two or three, we name it as ABC. So these are the random event, can happen anywhere, anytime. So on average, statistically, one event happen one day.
Okay, thank you.
Okay.
So thank you so much, ma'am. Thank you so much.
Thank for giving me this opportunity. Okay.
I request everyone to stand up for national anthem.